So in this lecture, we will learn about force due to unbalanced masses. So let's begin with the first type. That is called rotating imbalance. Rotating unbalance. So let's draw the semantic diagram for this case. Okay, so suppose there is a system which is mounted to some spring and the damper to some base structure. So this is the base structure, and the system consists of like a mass and fixed inside it. So this is some mass, so this is some mass which is rotated with some angular speed omega, and this is the reference point. From there is displacement x, and the force which is subjected to this rotary mass is me omega square sine omega t, and this is the base. Now the whole system looks like something like this. If we plot this diagram something like this. So this is the mass m, and from the figure you can see that the force is subjected to me omega square sine omega t in y direction, and suppose this is theta, which we can say omega t, and the whole system is rotating with the angular speed omega, and in the y direction the component of the force will be me omega square cos omega t. So what is the nomenclature? So let's understand the nomenclature for this case first. So so here capital M is the mass of machine, small m is the mass of rotor, and small e is equal to the eccentricity of the rotor. So the equation of motion in this case, we can write it as F inertial plus F damped plus F due to spring is equal to F unbalanced. So after further simplifying, we get capital Mx double dot Cx dot plus Kx is equal to small m, this is small m, let me make it more simpler to avoid any confusion. This is small m, me omega square sine omega t, which is further equal to f naught sine omega t. Sort of further simplifying, we are going to get f naught is equal to me omega square, f naught equal to me omega square. So we know that the dynamic amplitude is equal to f naught by k divided by, let me erase this thing first. So we can write the dynamic amplitude. The dynamic amplitude is equal to me omega square, small me omega square, divided by k divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So we know that omega n is equal to under root k by m. So we can, which is that is equal to m dot capital M dot omega n square is equal to k. So for further simplifying, we are going to substitute the value of k here. So we are getting the equation as x is equal to me omega square upon capital M omega n square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So if you are going to further simplify, we are going to get is equal to small m dot eccentricity divided by m capital M dot r square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So this is the amplitude for the case of rotating unbalanced. Now moving to the reciprocating and balanced. Let me raise this thing first. So in this case, let's think about this thing. This is the reciprocating and balance. This is the second case. Reciprocating unbalance. So let me plot the whole diagram in this case. So this is the reciprocating system. So this is the hinged, this is the hinge, this is some rod and which is attached to some mass of m, and this system is mounted to some spring and the damper which is attached to some base here. So this is the angle theta. So this is theta angle, and there is some angular rotation of omega speed, and there will be some displacement from the reference point, that is x. So the spring constant for this case is k, and for damping coefficient is c. So here small m, here small m is equal to mass of the slider, mass of the slider, or piston, that piston which is the that is the mass of the reciprocating element, and r1 is the crank radius, r1 is the crank radius, omega is equal to angular speed of crank, and it is constant, and it is constant in nature, and capital M is the mass of the machine, mass of the machine. So the F unbalanced, that is the unbalanced force, is equal to inertial force of the slider, which is equal to mass and acceleration of the slider, acceleration of the slider. So after further simplification, we are going to get mr omega square cos theta plus cos 2 theta by n. So if n is very large, so we can neglect cos 2 theta by n, so we can neglect it. So the equation becomes F unbalanced is equal to mr1 omega square cos omega t. So let's now use the equation of motion. So by using the equation of motion, which is F inertial plus F damped plus the force due to spring is equal to F unbalanced. So in this case, capital Mx double dot plus Cx dot plus Kx is equal to mr1 omega square cos omega t. So we know that F naught is equal to mr1 omega square. So let's calculate the dynamic amplitude. So the dynamic amplitude can be let me erase this thing first. So the dynamic amplitude is equal to x is equal to mr1 omega square divided by k, which is further divided by under root of 1 minus r square whole square plus 2 zeta r whole square. Here k is equal to capital M dot omega n square. So after substituting the value of k in this expression, we are going to get x is equal to small m r1 divided by capital M is equal to omega square dot omega n square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So when we are going to substitute um, this thing. When we are going to simplify this thing, we are going to get the dynamic amplitude as x is equal to small m r1 by capital M multiplied by r square frequency ratio, that is frequency ratio, divided by under root of 1 minus r square whole square plus 2 zeta r whole square. So one thing you should note that the in case of in case of in case of rotating imbalance in case of rotating imbalance in case of rotating unbalanced, the frequency of displacement, the frequency of the frequency of the displacement of machine or the displacement of machine will be equal to angular speed will be equal to angular speed of rotor. While in case of reciprocating unbalance, the machine will oscillate with a frequency equal to angular speed of crank, with frequency of equal to angular speed of crank. So the rotating imbalance B is equal to capital X upon small me by m, which is equal to r square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. And a reciprocating unbalance B is equal to capital X upon small m r1 by capital M is equal to r square divided by under root of 1 minus r square whole square plus 2 zeta r whole square. Now there are some special cases. So the first case is that if r equal to 0, so if r is equal to 0 and that is omega by omega n is equal to 0, that is, so we can say that omega is equal to 0 and b is equal to 0. Now the second case is r equal to 1, that is at resonance condition. We can say in this case b is equal to 1 by 2 zeta. Now let's talk about the third case. So third case is when zeta is equal to 0, that is it is the condition of undamped system. Undamped system. So in this case, P is equal to r square by 1 minus r square. And if r equal to 1 and zeta equal to 0, then for this case, beta is equal to infinite. So this marks the end of this lecture. So for now, thank you.